Alright, example 5 is about an angle changing. So we have a changing angle of elevation. Find the rate of change in the angle of elevation of the camera shown in the figure at 10 seconds after liftoff. So it says here we have a television camera at ground level is filming the liftoff of the space shuttle. That is rising vertically according to this position equation. S equals 50t squared. So as time goes by, we take the number of seconds, we plug it in and square it, times it by 50, and that gives us S, the height the rocket is from the ground. Where S is measured in feet, T is measured in seconds. The camera is 2,000 feet from the launch pad. So here again we have a triangle, we have our angle theta here, and the bottom of this triangle is 2,000 feet, and we're looking at this height here is S, the height of the shuttle off the ground. So we need to come up with a given rate, what we want to find, and the equation that ties it all together. They threw a little twist in here. Did they give us a rate in any of this? No, not really. But if we look at this part here, we are given a position equation. S equals 50t squared. Can we derive both sides of this with respect to t? Yeah, well, if we derive the left side, we have ds dt. And now we are deriving with respect to t, so there's not going to be, a differential created here. We just derive 50t squared and get 100t. So there is our given rate. It was sort of hidden, but ds dt is 100. I'll come up here. Given rate, ds dt is 100t. Now, another thing to think about on this problem is we are looking at a snapshot in time. Find the rate of change in the angle. So we want to find how this angle is changing. If this is an automated camera, you got to program in how fast the angle changes. When the shuttle's just taking off, that angle will be rising pretty quickly. But as it gets higher and higher, the rate of change of that angle is probably going to be slowing down. Let's see here. Find the rate of change in the angle of elevation. So they're asking us to find what? D theta dt. Oops, that's a theta. D theta dt is equal to what? And we do have our snapshot in time. When t is equal to 10. And we need an equation to tie all these variables together. And if we look at the picture here, I got to remember to take that out of the notes there. That's just giving it away. What ties this angle here into the sides of the triangle? Well, the two sides that we are looking at, here's our angle. We're interested in the side across from that angle and the side that is adjacent. So what trig function deals with opposite and adjacent? Well, that's tangent. The tan of theta equals opposite over adjacent. And here our opposite side is S, and our adjacent side is 2,000. So here's our equation, the good old trig function tangent. The tangent of theta equals S over 2,000. So let's take the derivative of both sides. So the derivative of tangent is secant squared. Secant squared of theta equals, and this is S over 2,000, or 1/2000th S. So when we take that derivative, the 1/2000th is a constant multiple. What is the derivative of S with respect to t? Well, the derivative of S would be 1, and then the chain rule would say ds dt. Okay, and let's see here. And I did forget something here. We are deriving with respect to t. So the derivative of tan theta would be secant squared of the same theta, and then we would have, by the chain rule, d theta dt. So I'm just going to scooch this over and add in d theta dt. Because that is what we're trying to find. D theta dt is what we're looking for. So I want to isolate that. How do we get rid of secant squared? Well, I can multiply both sides by 1 over secant squared, and that would cancel that out to a 1. And another way to write 1 over secant squared is cos squared. So I'm going to have my d theta dt is equal to, I'm going to multiply this side times cosine squared. So now I have a cos squared theta over here, and then I have my times 1/2000th, and then I have my ds dt. Okay, so I think we've derived both sides. Now we should start thinking about, plugging values in, values that we know, or values that we're looking for, trying to solve for them. Oops, and I think I might need that before too much longer. Ooh, yes, actually I am. Okay, ds dt, we could get around to plugging in for that, but beforehand, we've never dealt with one of these trig functions before in this problem. We have a cosine squared here. If we are going to start plugging stuff in, we got to substitute something in for this cosine squared. And if we go back to the original triangle, the cosine squared of this angle, or we need the cosine of this angle. And cosine is adjacent over hypotenuse. We have this side as 2000, that's not changing. But we are going to need this side of the triangle. We're going to need the hypotenuse. And what would this hypotenuse be? Let's come back here. If we're just going to do the Pythagorean theorem, s squared plus 2000 squared is equal to hypotenuse squared. Hypotenuse squared. And if we just want the length of the hypotenuse, we're going to take the square root of both of those sides. So the hypotenuse is the square root of s squared plus 2000 squared. So this cosine here, let me move down d theta dt, we have a cosine squared. And we replace that cosine with adjacent over hypotenuse. The adjacent side is 2000, and the hypotenuse is what we just come up with in that radical, the square root of s squared plus 2000 squared. Let me make sure we can see that squared. So the cos squared has been replaced with this. Remember, this is a snapshot in time. We are going to plug in something eventually for that s. And then we have our 1/2000th and ds dt. I think I might be able to move that picture out of the way to give myself a little more room now. Or maybe not. But we're going to start plugging in stuff now. We've derived, and we derived both sides implicitly. We did plug in something for the cosine value, that cosine of theta we replaced with this. Now we are ready to start plugging in anything else we can. So d theta dt. When we are looking at a snapshot in time, the angle of elevation, back to the original problem, 10 seconds after liftoff. So we have the side of that triangle S equals 50t squared. Well, then what is S after 10 seconds during our snapshot in time? So for t, we plug in 10 and we square it. 10 times 10 is 100. 50 times 100 is 5,000. So S is 5,000 at this instant in time that we're checking the change in this angle of elevation. So now we have, and we'll underline it in red, when t is equal to 10, and also when s equals 5,000. That's our snapshot in time. So back to here, d theta dt is equal to, here we have this, 2,000 over this under the radical quantity squared. Well, if we square that, our numerator will be 2,000 squared, divided by the square and the square root cancel out. So the radical's now gone, and we have s squared plus 2,000 squared. And now we know that s is 5,000 squared plus 2,000 squared. And I'm starting to run out of room. We still have this 1/2000th, 1/2000. Oops. And then on the end of this, we tack on ds dt. ds dt was 100 t. Let me get this out. I suppose I can get rid of this. The last part, ds dt, that's right here. That is 100t, and t is 10. So this is going to be 100 times 10, or 1,000. So we got to tack a times 1,000 onto the end of this. Times 1,000. And this would be a good time to just let the calculator do the work. Remember to parenthesize off your denominator there. We're dividing 2,000 squared by that bigger number times this 1/2000 times 1,000. You can just plug that in as a 0.5. Or if you leave it in if you do it on your TI-89 and you leave it in fraction mode, you get 2/29. And how do we measure angles? In radians. And we are changing with respect to time in seconds. 2/29 radians per second is how fast that angle is changing 10 seconds after liftoff. Again, that will be slowing down as that rocket climbs higher and higher. Of course, we save the best for last. Example 6, the velocity of a piston. In the engine shown here in the figure, a 7-inch connecting rod is fastened to a crank of radius 3 inches. The crankshaft rotates counterclockwise at a constant rate of 200 RPM, revolutions per minute. Find the velocity of the piston when that angle is pi over 3 radians. So here, this this is rotating counterclockwise, and you know the length of this arm. This is 7-inch connecting rod, so that rotates around, and as that rotates around, that connecting rod pulls and pushes this piston back and forth. Let's see here. The radius here is 3 inches. So here we have a triangle sort of pulled out, you know, a scaled down version. Here's our, the crank is 3 inches radius. Here is the 7-inch connecting rod. And this radius, or this angle, is changing. You know, this is rotating counterclockwise. So that angle is constantly changing, and it's going around at 200 revolutions per minute. We want to find the velocity of the piston. How fast is the piston moving and in which direction when that angle is 1/3 pi radians. Okay. So let's try to figure out our given rate. And I guess I shouldn't have moved that stuff up there. What is the given rate? The crankshaft rotates counterclockwise, 200 RPM. So what is changing is, the angle, d theta dt. That angle is changing with respect to time, and it's 200 revolutions per minute. Well, each revolution is 2 pi radians, so 2 pi times 200 is 400 pi. 400 pi radians. What are they asking us to find? The velocity of the piston. You know, the piston would be, you know, attached right here, and it would be sliding back and forth. So it's all related to this variable x. As the piston moves away, x grows. As the piston gets closer, x shrinks. So we're trying to find dx dt at a given point in time when theta is equal to 1/3 pi. Now, what is the equation that ties it all together? In the previous one here, we used a right triangle. Here, we used a right triangle with the Pythagorean theorem. This one was based on the trig functions since we were looking at an angle. This is also, we're looking at an angle, so we're going to have to go all the way back to pre-calc, the law of cosines. You know, this is for non-right triangles. B squared equals A squared plus C squared minus 2AC times the cos of the angle theta. Well, some of this stuff we have known values for that will not change. So our equation is, if we apply this ABC to the picture above up here, B squared is going to be that 7, so it's going to be 7 squared is equal to A squared, A is 3 squared, plus C squared, and that's our side x squared, minus 2 times A, and A was equal to 3, so that's going to be 6, times C again is x, cosine of theta. Let me make sure I got that right. 7 squared plus 3 squared plus x squared minus 6x cos theta. Yep, that's it. Okay. So there's our equation. And let me see if I can clear myself a little. Oops. Clear myself a little more room. This problem does get a little involved. So move this up here. Now we want to take the derivative. Ooh, this should be interesting. Derivative with respect to time. Well, 7 squared is just 49. That derivative is 0. 3 squared, that derivative is also 0. The derivative of x squared with respect to time is 2x dx dt minus, here we have, and I guess I could, this is 6 times x times cos theta. So we have minus 6 times. And now we are going to have here product rule. The derivative of our first term is a 1. The derivative of cosine is negative sine theta d theta dt. d theta dt. And the derivative of x would be 1 dx dt. Get that out of there. dx dt. That's a little better. So, product rule. First times the derivative of the second. X times this negative sine theta. So it's going to be negative x sine theta d theta dt. First times the derivative of second plus second times the derivative of the first. Cos theta, cos theta times dx dt. And, don't forget we do have this minus 6 out here. We can distribute that. Yeah, let's even do that right now. So we have our 0 equals 2x dx dt. This minus times minus will be a plus 6x sine theta d theta dt. And then negative 6 times that plus 1 will be a negative 6 cos theta dx dt. And we are trying to solve for dx dt. So let's see here. I have this term has a dx dt in it. And this term has a dx dt in it. So I'm going to move them to the other side of this equals, change their signs, and factor out the dx dt. So I will pull a dx dt out of each term. And when this 2x moved over, it became a negative 2x. And when this negative 6 cos theta moved over, it became a positive 6 cos theta. And I factored that dx dt out. And that's equal to the 6x sine of theta stays right there with the d theta dt after it. d theta dt. Okay, I don't want to get rid of too much here. Actually, let me just do this. And we're solving for dx dt. I missed that parenthesis. So now to get dx dt alone, I'm going to divide both sides by this. dx dt is equal to, we'll have our 6x times the sine of theta d theta dt. And then we're dividing both sides by this quantity. And I don't like that negative first. I'm going to put the 6 cos theta first, and then minus 2x. And that's our quantity that we're dividing by. Okay, so we've derived both sides. We're ready to start plugging some stuff in. But this sine of theta and cos of theta, yeah, I guess we're just going to plug in the pi over 3 radians for that. But we are going to need to solve for this x here. We have 2 times x. Up here we have a 6 times x. And if I remember, they did not give us x at all. No, they didn't. But we can find it. Our original equation, highlighted here in green, we're at a snapshot in time. we can take this equation, plug in what we do know, and then solve for x. So what I just highlighted here, I'm going to flip to the next slide, and for this, the cos of theta, we're going to do this as the snapshot in time when theta equals pi over 3, and then we'll just solve for x. So now we have to solve for x. So that equation was 7 squared equals 3 squared plus x squared minus 6x, and then we had, what was that? The cosine of theta. And now it's going to be the cosine of pi over 3. And if we remember our unit circle, the cosine of pi over 3 is 1/2. So that'll be 6x times 1/2. So we have 49 equals 9 plus x squared minus 3x. And we're going to get everything on one side. I'm going to move the 49 over, subtract it from each side, and then we'll have x squared minus 3x minus 40 equals 0. So we need to factor x squared minus 3x minus 40. That does break down nicely into two factors. We have an x minus 8 and an x plus 5, and those are equal to 0. So we set each factor equal to 0, and we get 8 or negative 5. Now, which one of those answers does not make sense? Remember, this x, what does x represent? X represents the distance away from the piston. So is x ever going to be negative? That's a length. Can we have a negative length? No. Negative 5 does not make sense. So at our snapshot in time, x is equal to 8. So x equals 8. And theta equals pi over 3 are what we need to substitute now. So back to here, we did all that work just to solve for this x and this x. And now we can start plugging some stuff in. dx dt is equal to 6 times x is 6 times 8. Sine of theta is the sine of 1/3 pi. d theta dt was given to us. That was 400 pi. That was our RPMs. Divided by. Down here we have 6 times the cos of theta, or the cos of pi over 3, minus 2x, or 2 times 8. Okay. Might as well, just finish this off real nice here. And I'm getting sick of red. We'll switch back over to black. This is dx dt equals 6 times 8 is 48. The sine of 1/3 pi is root 3 over 2. 400 pi, we'll leave that in terms of pi, all divided by 6 times the cosine of pi over 3. Cos of pi over 3 is 1/2. Minus 2 times 8 is 16. And if we clean that all up, it's going to look like this. 9,600 pi times the square root of 3 all over negative 13, which is approximately negative 4,018 inches per minute. Remember, we were trying to figure out the velocity of the piston. Let me see if I can get that to the front. The piston's traveling back and forth. We were trying to find the velocity at that, instantaneous moment in time. And our answer turned out to be negative. What does the negative tell us? Well, it tells us that the piston is heading toward the left. When this angle is pi over 3, as that goes this way, this length 7 never changes. That's pulling the piston back towards the crankshaft. And exactly how fast? 4,018 inches per minute. Remember, that negative just tells us the direction. So that was a doozy. But are you crying? There's no crying in math class.